So our third speaker now is Sven Beyer from OneSpin Solutions, and he's going to talk about formal verification of a hardware unit. So hopefully I'll unmute Sven and I'll make Sven the presenter. So you should now be the presenter, Sven.
Okay, Mike, thank you. And I hope you are now seeing my screen.
Yeah. Yes, we can see your screen and we can hear you. So I'm going to mute myself and let you go.
Perfectly. Good. So actually, I guess the title somehow got a little bit simplified when putting into the overview here. So of course, I'm also looking at safety-specific application of formal verification. So let me briefly start. Also, since we are not, since we are kind of pressed for time, so I'm not going to do too much of a motivation, right? So you are in this webinar, so I'm pretty sure that you are aware of problems related to safety. And let's just look at this in a little bit systematic fashion and look at the reasons why things break, which also have been hinted at already by Holger and by Mike. So of course, on the one hand, you have the systematic errors, which can be things that have been already in the design, so put in by the human, so functional bugs, if we are in the hardware world, in the RTL. But even if the RTL doesn't really have any functional issues, could still be systematic errors because the tool flow or the synthesis actually introduced problems that end up in the chips that are not in the RTL. So that's the one big category, the systematic problems, and the other ones, and of course the systematic errors is more the traditional things that verification has cared for quite some time. But there's also the random side of problems in the field where things just, even if they actually should work, because everything is right in the chip, something due to radiation or stress, whatever, it gets corrupted in the field and produces, again, faulty behavior. And of course, there are lots and lots of standards. I'm also not going to the details here. It's already been mentioned previously that try to address all these different topics and make sure that the best possible verification is done for areas where it is critical, like automotive, nuclear, aerospace, and whatnot. Now, what are the different techniques that are used here for performing these verification tasks? So on the one hand, you have the systematic errors, right? And that's where all the traditional verification is applied. So you do your traditional functional verification. And in addition, you also typically, right, you have to make sure that your synthesis flow didn't introduce anything. So you use, for example, equivalence checking to make sure that whatever ends up in the final post place and route netlist does not have any less functionality or corrupted functionality in comparison to what you had before on the level of RTL where you did your verification. And on the random errors, of course, additional verification is needed, and not only verification, but also, of course, qualification, because at the end of the day, you need to ensure that you have hit certain criteria with your safeguarding mechanism against the random errors. And of course, as Holger already pointed out, all this has to be put together with the market requirements and making the problem of designing today's chips with all these safety measures a really tough challenge. And this is actually where we think, and also lots of companies and industry who are involved in safety think that formal actually is a new methodology that can have an impact there and help you a lot in actually achieving these safety verification tasks that you have to carry out. And actually, formal can actually be applied in quite a lot of scenarios that are required. Namely, that you can look at the traditional equivalence checking, just making sure that your synthesis doesn't introduce anything or doesn't optimize away any of the safety functionality that you have put in. Then, of course, if you look at the human errors, formal is a well-established way to make sure that you get a very good functional verification on your RTL side already. But also formal can play quite a role in actually the really, I would call it core safety verification, where you actually look at the safety functions that you have implemented and whether these safety functions do a proper safeguarding. And finally, also on the qualification side. So formal techniques nowadays also are very well suited to assess how much you have verified, on the one hand on your normal standard functional verification, but also to assess your specific safety verification task and qualify them. Now, that's the example actually, right, as the arrow here points out. So that's the thing I want to focus on today in this short slot, on the additional safety functions you put in for the random errors and the safety measures and their verification then with formal. Now, right, so you have the typical picture, you have the normal behavior, and at some point a fault occurs. So something gets stuck in the design, some bit flips or whatever, and this is something that can happen, right? It's impossible to ensure that it doesn't happen, so the only thing you can do is to actually safeguard against it. So make it very likely that this actually gets detected, hopefully even corrected, but at least, yeah, make sure it does not lead to unpredictable behavior. So in addition to the functionality you have to put in anyway, you put in additional functionality to ensure this particular purpose. And of course, a general observation here is it's possible to safeguard against all possible random things that can happen in the field. You kind of have to focus and make sure then with coverage and whatever that you did a good enough job. Right. So you detect faults and, if possible, try to correct them. And how is this done? Well, there are different techniques, of course, like putting in specific redundancies, so duplicating things, and in order to detect mismatches between the duplicates. Then, of course, you have the traditional error correction code mentioned already by the previous two speakers, specific encodings. And then, of course, you have lots and lots of stuff on error management units and alarm detection stuff to make sure that whatever you detect actually gets proper attention. And what you typically also do then is kind of just regularly self-check this functionality on the live chip to make sure all your safety functionality is still working and it's not happening that some part of the safety management functionality, like some part of the error management unit, is just affected by some random error and therefore is not doing anything anymore. And of course, the problem here is all this stuff that you put in, it does not happen in normal operation mode. So your normal simulator and your synthesis tool actually would think this is kind of redundant stuff. It never triggers or it doesn't affect I/O behavior. So actually to verify it properly, you need to inject faults in your design and perform additional verification with injected faults. And we pick here a very simple example, just also looking at ECC. So because also RAMs are a big area, and so there's a high probability that some data in RAM gets corrupted. So typically what you do, you add a couple of additional bits to the data in the RAM with specific error correction codes. And later on, then decode the stuff in order to figure out whether the data was corrupted. And the typical stuff here is you have the classic 2-bit ECC. So you detect and correct the 1-bit faults. So you may even flag the corrected faults so that it at least gets recorded in your chip that there was a fault, but it was corrected. And you're still able to detect any 2-bit faults. So in this case, the data is corrupted. So it's really crucial that in this case, some specific error handling mechanism is triggered. Now, how would you approach this verification then on the simulation side? Well, you actually have to deal here with a large number of possibilities. So it's not just what you have anyway already on the functional verification side, but you also consider then all kinds of possible faults. So there could be a fault in each potential bit. And of course, you're not only looking at 1-bit faults, but just 2-bit faults in 256-bit data. Well, it's quite a lot of combinations of errors that you actually would have to simulate if you stay here just in the simulation world. And this is exactly one of the areas where formal can make a huge contribution, because here you have the possibility to just apply a certain, what we call here in this picture, error model. So you consider all possible error locations. So in the typical nature of formal, right, you say, okay, I have potentially an error on each bit. And then you say, okay, if I only have an error on 2 bits, can it then happen that the error bit is not activated? And formal does what formal does best. It is looking for the inputs for you. So inputs in the traditional normal sense, so the inputs of the design that produce something, and also the errors to be injected to produce something. And if in any way this can go wrong, so if there's any particular data and any particular 2 faults such that the error flag is not raised, formal will find them and just show them to you in the simulation trace. And if these things do not exist, well, formal can give you really a proof that this mechanism works. So all 2-bit errors are actually detected. So that's the big advantage that you have with formal verification over a simulation approach. And for that, we actually have built a specific app. So it's the term typically used these days for small customization layers of the tool, so to speak. And basically, you give it a number of candidate bits, so places where you want to consider faults. Because again, right, you can't safeguard against everything. So you have to have an idea when you design a mechanism against which faults it's supposed to safeguard. And what this app is then going to output is a setup that allows n-bit faults of specific types. So you can also configure types of faults that you want on these particular candidate bits. And then the thing that you as the engineer need to do is to capture the intended behavior of the 1-fault behavior or the 2-fault behavior in a specific assertion, right? So you wouldn't write an assertion saying, oh, in the 1-fault case, I get the right data and the detected output is actually activated. And for 2-bit faults, I get the error output raised. And that's basically all there is to it. And if you do that and apply it to also industrial size designs, you actually get quite nice performance with a single assertion. You can get the full confidence for this specific sample of an ECC correction mechanism from Infineon in a few minutes. And of course, here we have the concrete number, I think, for single-bit errors, but for 2-bit errors, the numbers are quite similar. So testing hundreds and hundreds of thousands of faults on billions of data values and getting the full confidence that the mechanism works. Now, to sum up, right, so any of these random errors, you just cannot avoid them. So you add specific safety functions to detect and maybe also correct them. And yeah, this adds another exponential explosion to the verification complexity, which makes it really kind of impractical to tackle in simulation. And therefore, formal verification really lends itself very nicely as a new player here in the safety market, because you really just model classes of faults and candidate bits where faults should be injected, and then you can perform exhaustive verification for these specific mechanisms. And other stuff that I did not mention here due to the time restrictions is also, there's also the possibility to qualify this stuff. So you could also then ask the question, okay, which types of faults or which code was actually covered in this particular fault analysis and which was not. So yeah, additional, making sure you meet the additional requirements that you actually have from the standard then for the qualification of your fault analysis. And yeah, quick summary. So of course, this was a very short version of this safety topic. And as you can see from the slide number 34 that we've reached here, there's actually quite a lot more material and also a demo there. And if you're interested, actually, we're also going to present at Design Automation Conference this year. And we have also some session there also joined with Mike, if I remember correctly, on requirements-driven verification that, where there's definitely more information to be had on this topic. So I guess now I'm open for questions and pretty much on time.
Yes, we are on time. Thank you, Sven, for that. As it's fairly obvious in these webinars, it's difficult to present all the information. So as Sven's done here, there will be more information available online for a lot of these. So we have one question from J.M. Foley, but I'm not sure I can. Let's see if I can unmute you, J.M.
Oh, I just muted myself. So.
Hello, J.M. Foley. Jean-Michel. Yeah. Do you want to ask your question?
Yes, I have a simple question. I understand from the standard that a number of those things has to be done at gate level, for example, for diagnostic coverage. So what is onboard here, is it at RTL or at gate level?
Very good point. So actually, so we have a tool that also has equivalence checking. So on the one hand, we can do equivalence checking between RTL and netlist as well. But on the other hand, what I showed here can be carried out also on any level where you want to carry out the verification. You can do it on the RTL, but the same formal techniques can be applied also on the netlist. Post, place, and route netlist or whatever, so as close to the synthesis result as you need to get for your certification. So that's basically open, and whatever you need to do, you can do with this approach.
Okay, thank you. We have one more question. I think we just have time before we move to Neil Langmead. And the question is from Wouter van Vent. Apologies if I pronounced that wrongly, Wouter. How long do double fault simulations take if single fault simulations take 5 minutes?
Well, that's a good point. So in this particular example, I don't have the data. In the demo, we would have been showing a smaller example where basically everything runs through in a couple of seconds. So I would assume it's in the same order of magnitude as the single bit faults. Because you have the complete freedom anyway on which fault you look at. So it's typically not much longer.
Okay. Thank you, Sven. Just in order to stay on schedule, I'm going to say thank you very much to Sven. Thank you for your presentation. Again, that will be online with more information as well, both the slides and the recording.